Okay, well, now consider this /26 subnet mask. The IP address is exactly the same. What has changed is that instead of 24 bits for the network ID, now we're using 26. In this example, the network ID uses the first 2 bits from the last octet. Now, this arrangement is a little bit more difficult to visualize if you're thinking of it in decimal form, because the last octet is partially dedicated to the network ID and partially dedicated to the host ID. In binary, however, it is simply just a 26-bit number instead of a 24, and the host ID is 6 bits long. This is a small table of slash notation and the corresponding binary notation, and also the corresponding dotted decimal notation. And if you are thinking you need to memorize these, you're right. The only way that you can be successful at understanding and working with IP version 4 addresses is to know these numbers by heart. There's 9 of them, and they repeat. So as you can see here, this is for /16, and the first 2 octets of ones is 255, 255. Now /17 takes the first bit of the next octet, and that number is 255, 255.128. The second number, the third octet, is 192. The /19 number, the third octet, is .24, and /20 is .240, and then 248, 252, 254, and 255. And you should know the conversion just by looking at the numbers. So if you see /24, you should know that that's a 255, 255, 255 number. If you see a /20, you should also know that that's a 255, 255.240 number. Rarely you will see it in binary notation, but you should know that as well. Here's another aid that will help you learn the binary numbers converted to decimal. And you should know these sequences forward and backward so well that when you look at a number such as, say, 224, you know that when moving from left to right, this value is the third after 0, and is therefore 3 bits removed to the right from 0. The 0 octet value, that is. In the same way, you need to be able to look at 248, say, and know that when moving from right to left, this is 3 places before 255, and it is therefore 3 bits removed to the left from 255. Okay, this is the subject of converting between binary and decimal notations. It won't be that often that you need to do it. Mostly you would have a scientific calculator that will allow you to do the math. However, I believe it is important that you understand how to do it in your head or in a piece of paper with a pencil if you do not have a calculator. It will certainly help you understanding IP addressing. With that being said, first let me explain how come 2 to the 0 power or 10 to the 0 power equals 1. Down here you can see that 1 equals 4 over 4. That's easy to understand. Anybody could agree with that. That is also equals to 2 to the second power over 2 to the second power, because 2 to the second power, or 2 squared, is 4, and 2 squared on the bottom is 4. It's the same as 4 over 4, which is the same as 1. But that is also equal to saying 2 elevated to the power of 2 minus 2, which equals 2 to the 0 power. In turn, we can say that 10 to the 0 power is also equal to any number to the 0 power will equal to 1. Well, I hope I didn't confuse you, but let me go to the base 10 that we're familiar with and see if we can look at it a different way to make it easy to understand. In a base 10 system that we use every day, in scientific notation it works similarly to the binary system. So we have 10 to the 0 power, which equals 1, and 10 to the first power, which equals 10, and 10 to the square, which equals 100, and cubed equal 1000, and so on and so forth. But if you notice, the pattern is 10 to the 0 is equal to a 1 without any zeros or 0 zeros. 10 to the 1 is equal to a 1 with a 0. 10 to the 2 is equals to a 1 with 2 zeros, and 10 to the 3 is equals to a 1 with 3 zeros, and so on and so forth. So 10 to the 6, it'll be equal to a 1 with 6 zeros, or 1 million. Now, that's easy to understand because that's how we do math every day. In a binary system, however, if we look at the scientific notation, it works exactly the same way, except that instead of incrementing each time by 10, we double each time we go up in the coefficient of the number. So 2 to the 0 equals 1, 2 to the 1 equals 2, 2 to the 2 is 2 squared equals 4, or 2 times 2, 2 to the 3 equals 2 times 2 times 2, which is 8. But if you notice, is each time it doubles. 1, 2, double 2 is 4, double 4 is 8, double 8 is 16, double 16, 32, 64, and 128. Now if you notice, the next number, if we had a ninth bit, it'd be double 128 or 256. Now what I wanted to get at is that for any number, if you have all the ones before filled with ones, it'll be the last value double minus 1. In this case, if we had another 2 to the 8th, it'll be 256. But since we don't have 256, adding up all these numbers, it's 256 minus 1, or 255. I don't want to confuse you, but you should study these two tables and make sure you understand how it works. Okay, now let's try a binary to decimal conversion using a simple conversion table that you can draw by starting with a 1 and proceeding to double the resulting number each time to obtain the 8 values of an octet. Then we will try to convert this number to decimal. Okay, so to get the values, what you do is you start with 1 and you go doubling. The first number is 1, then 2, you double that, it's 4, you double that, it's 8, double that is 16, 32, 64, and 128. That gives us the 8 values of an octet. Okay, we have the 8 values for each bit for our 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. And now we have this number 10000011. And I put it right here, 10000011. Now, to convert the value from binary to decimal, what we need to do is to add the values for each bit that has a number 1. In this case, the leftmost bit has a number 1, so the value for that is 128. We do not add to that 64 because it's 0, and all these values that are 0 we don't need to add. So we add to 128 2 because we have a 1 on the number 2 value. That makes it 130, and then we have a 1 in the 1 position, so that makes it 131. Therefore, the binary number that we have right here equals to 131. Okay, now let's try to convert a decimal number 209 to binary. The first thing you should do is draw the conversion table that we just used. The next step after you set up the table is to consider whether the highest value, binary value that you have, is it larger than the number you're converting, or in this case 209. Our largest number is 128. So the answer is yes. So we're going to place a 1 right below that. I'm going to paste it over here. So that's what it would look like. The leftmost bit is set to on or to number 1, and that gives us a subtotal of 128. Now the next question is, what's the next value after that? It's 64. If we put a 1 under 64, we would have to add the 128 to the 64. Now adding 128 and 64, is that greater than 209? 128 and 64 is 192, so the answer is not greater than 209. So we will place a 1 under the 64 value and add that number to 128. Then when we do that, we have 128 and 64, and here's the subtotal, and that equals to 192. Now we're not at 209 yet. Next we will contemplate the 32. If we add 32 to 192, is that going to be less or more than 209? Well, I can tell that's going to be more than 209, so we cannot use a 32, so we'll put a 0 in the 32 position. Now if we add 16 to the 192 we have, is that going to make the number larger than 209? So 192 and 16 is 208. No, it's not. So we will put a 1 on the 16 position and a 0 on the 32 position. So this is what it looks like once we do that. We have 128, 64. We do not have 32 because we have a 0 in its position, and then we have 16. If we add all those values, we end up with 208. Now we're trying to get to 209. From here you can see it's easy. We're not going to have an 8, we're not going to have a 4, we're not going to have a 2. We only need one more to get to 209 from 208. So the binary number would be 11010001. And the conversion is completed right here. Our binary number for the octet is 110 10001.